logs and exponentials. Derivatives.
Is it hard?
We do need to review logs and exponentials. We haven't seen that in a while,
Oh
so
my gosh.
probably since like 10th grade. Much. I don't think we did much.
I don't know. Last year was more.
Okay, so let's say I gave this sine line to you because you want to, because you can build the sine line. You just don't know how to sketch the graph.
Like at the very end.
I think.
That's all right.
Right. Okay, so let's say my f prime sine line looks like this.
Is that so F prime? It's like,
This is f double prime here.
oh, F double.
Hey. Just bring this up here. Here. On the slides. This spreadsheet. See that. Okay. Okay, so let's say I gave this to you here, and I asked you to sketch the graph. Okay. And let's say we've already, like you said, we've already built the sine line from the derivative graph. Okay. So we know how our graph is going to look. It's going to rise to -3, fall to 1, and then continue falling until it hits 4. Okay, wherever that graph it looks like. Now, let's say I gave you some order pairs. Let's say I give you order pair -6, 5, and then let's say I gave you order pair 4, -3. Right?
Okay.
-6, 5. Or -3. Okay, now the order pairs from here on out is not that important. It's really just sketching the graph to make it follow wherever the arrows are telling us. So what do we want our graph to do initially? This is the original graph.
No, rise.
Right. Okay, so we're going to rise until it hits -3, or the x value -3, however high that we may want that to be. It doesn't really matter.
Oh, so you start from, oh, okay.
Yeah, I'm just following whatever the arrow tells me. Okay, so what happens after -3? right? Wherever, just you can make the graph go to wherever at 1. It's going to flatten out for a moment because there's a slope 0 here. And it's going to continue what?
No, falling.
Falling to 4, right? The arrows are telling us to go down. Because this is my slope sign line. So whenever there's a critical point in between, that's telling me where there's a slope 0. So critical points is going to be anything in between. Because in order for my graph to rise and then fall, it's got to flatten out for a moment. That makes sense. Because how do I get those numbers? So we skipped the step of where I gave you the derivative graph, right? Because you said that you were good from the derivative graph to the sign line. So we pick up from the sign line because you say you struggle with this, right? So
how did you know, like, between the sign line, like those two? Or did you just say that they were the critical points for?
right,
Okay.
right. Because if we were to start at the beginning, then we would pull this information from the derivative graph. But I think you say you didn't want to start there,
Yeah.
right? Okay.
I'm good.
Okay, so you're good with the shape of this graph. Okay, so now what we have here, these are points of inflections. Or the -4 is point of inflection because there's a change in sign for concavity. Again, I'm not showing the derivative graph because you say you're good with pulling that information.
Yeah.
So now, but we do know that, yeah, these are points of inflection because there's a change in sign. So to kind of help us map our graph a little bit, we're going to find -4. Got this backwards here. No, you're right. Yeah, that's it. Sorry. This it's better fit if I put this around. So let's say I got these back rows and what we should be starting at concave up. Yeah, so I kind of had to look at the graph a little bit. Okay, so it doesn't matter where the points of inflections are, but well, in terms of the y value, but we know that the point of inflection is at -4 and 1. So wherever the graph lands at -4, just go ahead and plot that point. So we can kind of target that point as a point of inflection. And wherever your graph landed at 1, just highlight that point. That way, you're just going to connect the dots with the appropriate curves that it's supposed to meet.
So like once you plot.
Yeah, once you do your dotted line from your slope sign line, then
You plot the points.
Plot the points of inflection in between. Yep.
Okay. And they're just like on the graph, like it's on an X intercept, right?
Right, because that's not important. We just want to get the shape of the graph.
Okay, got it.
So now we want the graph to be concave up between -6 and -4. So it's a little bit of a U-shaped, right? But it's not going to be a full U shape because we don't have that path on this side. Okay. And then it switches to concave down. So we're going to make concave up. Oh, yeah. No, this is concave up, but the thing is, it's going to have to take on like this curve, this shape right there, right? Decreasing concave up. Now, I'm just kind of over exaggerating the curves so that we can kind of see it, right? So concave up, concave down, concave up. Now, let's say on my test that I also gave some information. Let's say I said the range of the graph should be from -3 to 9. Good morning, Sid. So range means whatever my end graph looks like, the lowest y value should be -3, which it is, but my highest y value should be a 9. That's right. I need to adjust. I mean, it's good to do this last because we don't want to do too much at once, but we can just, do whatever we can without looking at the range, and then we can look at the range at the very end and say, oh, okay, all right. So looks like my graph is a little low. So I'm going to just pull on it until it hits that 9. There's our graph. Now you're going to have to be able to sketch the original graph, and you're going to have to be able to sketch the second derivative graph. This is going to be off of, we're going to only build it off of the second derivative sine line. That's all we need.
For this,
Second derivative graph.
okay. Is that not the, you said we need to build the original? Is that not the original?
This is the original graph, but on the test, I'll ask you for the original graph and the second derivative graph.
I was like, is that the first?
Well, we skipped the first derivative graph since,
Okay.
we're halfway through the problem now, from the derivative graph to the sine line. Okay, so now the second derivative graph.
You only have to rely on.
That's right, you only have to rely on the second derivative sine line. But we're going to label so we know where to put things. Point of inflection.
Oh, so you put the points of inflection on the
X-axis.
x-axis on the second one, but on the first one you put it on.
You put it on, yeah, that's right.
Or like your graph.
Because point of inflection on the original graph is going to look like the transition from one curve to the other.
Okay.
But on the second derivative graph, it's going to look like x-intercepts. On the first derivative graph, it's going to look like peaks and valleys. What does that mean? So these are supposed to help us with our guides, to help guide our graph. So where should our graph live?
Oh, above.
Above. But the point is telling us that it has to come down.
Oh, yeah, that's what. -4 to 1 is concave down, so it needs to go
Below the graph. But which is going to make it a smooth curve. It's going to loop back up. Remember, this is the second derivative graph. So the shape has nothing to do with. I think that's what confused students. They're looking at this going, look, the shape has nothing to do with it. But what you want to do is you want to look at the location. You say, okay, as long as the location looks like it, then I don't care about the shape. Yeah. So just make it smooth. Just make it go up.
That makes sense. Wait, can we put arrows at the end because?
It doesn't. I mean, we don't know what the points are, so we can just have it stop.
Oh, but like you're not gonna take points off on the quiz.
No.
Okay. Back to the test. What page are we on?
Let's see.
Oh, is it page 21 where it's like morning listening?
Yeah, the morning review I'm gonna save for Monday. Oh, the test is Monday.
The test is Monday?
Mm-hmm.
Mr. Yang, I'm literally sitting here thinking this test is like during first period. Okay, see, hear me out. I was not here yesterday during class because I was taking my SAT. So was that an important information I missed?
I sent it out in the text remind.
Yay, I'm so less stressed. Mr. Yang, that's literally why I woke up at 6:30 this morning. And I'm like, oh, this test is first period. Mr. Yang, you almost gave me a heart attack. Don't ever do that to me.
I thought you got my text reminds.
I am, but like sometimes I have too many notifications going off, so
So you
sometimes
actually
my phone
fix
is
them
like
off.
do not disturb.
Got
And I
it.
miss important information clearly like that. Because I'm like, why is there no one here? Like, you know, the day of the test, everyone's just like piled in chairs and desks and no one's here.
Okay, you want to do an optimization one?
Yeah. I haven't done. I think page.
Have you done the one on 19? Because we did that
No.
yesterday. So this is similar to the one that we did in
What?
class.
Interesting.
Mhm.
I was like, you know what, this graph, I'm gonna know as much as I know right now. It's not gonna matter. That what we're doing in class today?
No, here's the calendar. We're gonna we flip flop Friday and Monday so that I'm not losing a day of instruction. So we're gonna start the next section. But if I put another review day in, then I'll be a day behind. So, but I wanted to give students extra day of review without losing a day.
You're just taking one more, I guess, two more tests before Thanksgiving,
Yeah, that's right.
because we're taking the church derivative test, I'm guessing after. Okay.
Okay, let me just create a problem then, because I think some of those students that they've done the one on page 19 already, so I'm gonna, hey. So let me on the scratch sheet here. Yeah, I'll write this problem here. Okay, so we want to create a box. Let's say the box. Is 2 times that of the base width. Rectangular box. Okay, this is the closed box, which means that how many sides is there going to be? 6 sides. Yeah. So Okay, so the bottom is most expensive. And the other sides are $4 per square foot.
We did lose a,
Yeah, no.
yeah, but we have basketballs. When you're that young, especially, probably. Yes. I'm just saying.
Okay, base length is twice that of the width. The bottom is most expensive. The material to create the bottom is $10. The material for all the other sides and the top is $6, sorry, $4. And then the box starts with a volume of 75 cubic feet. So here's our box. Okay, so I know that one side of my base is going to be shorter than the other side, so I'm just going to call one side 2x and the other side x. They don't, the problem doesn't give us any relationship involving the height, so I'm just going to call it h. Okay. So we're trying to minimize cost. Now the cost is going to come from the surface area and not the volume, because we're not paying for the space inside the box. We're paying for the material that is building that is surrounding the box, right? So surface area. We're going to build our surface area first, and then we can involve the cost into surface area once we get this going. Okay. So surface area, add up the area of all the surfaces. Okay. So let's start with the most straightforward one. What's the base area? Okay. Is there another 2x squared?
Yes, because it's close.
Okay, up there, up the top. Okay. 4 more sides to go.
Because there's one.
That's true, but are all the vertical sides XH? This side is XH, and then the other side is XH. What about this front side here?
Isn't it 2x?
Yeah. Okay, so now we're going to involve the cost, and that way we can update this equation and call it the cost equation. But we have to multiply the amount into the size that per square foot, right? So I'll choose the first 2x squared to be the bottom, the base, but everything else is going to be multiplied by what? 4. Okay, good so far. So I put a star next to the cost because this is what we want to find the derivative for, but there's something that's preventing us from finding the derivative just yet. There's something that's sticking out. The h. That h needs some help, right? We need some replacement for that h. So what we're going to do is we're going to create a secondary equation. And what secondary equation do we have that can help us build or replace this h? What information is given? Volume. But we need a formula for the box, for the volume. What's the volume formula for this box?
Base.
Mhm.
So it would be bases 2x.
Mhm.
Oh, so 2x squared times 8.
Okay, we'll work in the information that we gathered from the volume. We want to solve for h so that I can make a replacement here. $75 and 2, I'm going to reduce that to be 35. Or sorry, 37.5. The x squared stays below. No, good. Okay, so now we have our cost equation that we can update, and then we can eventually find the derivative for. Because now we only have one variable showing on the right side. Oops. I take out one of the x's. I'm left with one x below. Get it ready for power roll. Okay, so now I can find the derivative. So what's going to happen is if we find the derivative, we can find the optimal dimension of the box, which will minimize the cost. So there's all these potential dimensions that we can create. We're restricted because the box can create a volume of 75 cubic feet a lot of different ways, but we want to create it in a way where we're saving the most money. It doesn't matter what the shape of the box is in terms of, how wide or how tall, but we only restriction is 75 cubic feet, and we want to. There's a lot of different ways that we can create a box. We want the one that's going to cost the least amount. Okay, set the derivative equal to 0. Okay, cross multiply, solve for x. Yeah, I added the 900 over x squared to the other side so that I can divide by negative, but
Oh.
when both sides are negative, I can just take it out. Okay, so there is my, I took the cube root of both sides. So when x is 2.524 feet, I can find the other dimensions and then I can also find the minimum cost. So once you find x, you're pretty much near the end of the problem. You just have to be able to know what to plug in to find the information that the problem is asking for us to find. The problem is asking for to find the dimensions of the box. So I can find the length, the width, and the height using the x that I found. And then I need to find the cost as well. So I can plug into any of the cost equations. There's a bunch of cost equations, right? Because we were updating all these cost equations all the way down, but we can just choose the one that feels the easiest to plug into. Just make sure you don't plug into C prime. That's not what we want. We want the cost. So dimensions, if x is 2.524 feet, I can double that to find the width. And then I can also find the height because I have a height formula that I use halfway through the problem, 37.5 divided by x squared. Here are my dimensions. If I multiply this out, it should multiply out to be 75. Double check that. Really close, yeah. Right, there's a lot of different ways that three numbers can multiply to be 75, but this is the one that we want to choose because we know this is going to be the one that is going to the most cost efficient. Okay, so now we can find the cost, the minimum cost. If I insert the 2.524 into my cost equation, it's how much money that we'll be spending to create this box per box. Okay, any questions with the steps there? Okay. All right, let's go to review worksheet 2. Pick out some problems there. You skip number 1. Let's try number 2 on page 15. Okay, so let's do a derivative graph here. Given the graph of f prime, find the following properties of the function. So basically we're just going to create a first derivative and second derivative sign line. And then we'll sketch the function. And I think let's also practice sketching the second derivative graph as well. Okay, so if I'm looking at my derivative graph, the value that we see is not important, it's really the location here. So go ahead and label. So here's my first derivative sign line. Right, so I first pick off my slope zeros. So -1, 1, and 5. Don't look at the movement of the graph, look at the location. Between to the left of -1, my graph is clearly below the x-axis, so this is my guide here, negative slope. Right between -1 and 1, clearly above the x-axis, so positive slope. Between -1 and 5, clearly below the x-axis, so negative slope. And to the right of 5, above the x-axis, positive slope. Okay, so the arrows is going to basically tell us how our graph is going to move. We know the graph is going to dip to a relative min at -1, rise to a relative max at 1, fall to a relative min at 5, and then when x equals 5 and rise after that. Intervals of increase, decrease, relative max, relative min. We can just pull this directly from our slope sign line and write out our because statements. Relative minimum at -1 and 5, relative max at 1. Okay, points of inflection. The way we pick off points of inflection, if we're looking at the derivative graph, you're going to find the relative max, relative mins. Those are our points of inflection. So 0 and 3. But I'm going to create my second derivative sine line so I can have everything in front of me. Okay, to the left of 0, I want to look at the slope now. Okay, the slope of my derivative graph is going to translate to the curvature of my original cavity of my original graph. So whenever the graph is rising, my derivative graph is rising, that's going to translate to concave up on my original graph. Whenever my graph is falling, my negative slope there is going to translate to concave down on my original graph. So color coded here. Everything up to 0, my derivative graph is rising. So that means my original graph is going to be showing me a concave up shape. To the right of 3, positive slope is also going to translate to a concave up shape. Negative slope on the derivative graph is going to translate to a concave down shape. Okay, so points of inflection we can clearly see at 0 and 3 because there's a change in sign. Oh, concavity. Okay, so concave up, 2 intervals, and middle interval is concave down. Okay, to draw a sketch of the graph, let's split this up into 2 spaces here. One I'll do f of x, and one I'll do f double prime. I can go ahead and plot all my order pairs, and I'm just going to rely on my slope and concavity sine line to do the rest. Okay, so I'm just going to use a dotted lines to help me just get the shape of the graph going. Don't really care about the curvature right now. I just want to do whatever the arrows are telling me to do. Negative slope until I hit relative minimum. Positive slope until I hit my order pair 1, 5. Negative slope until I hit 1 or 5. And then positive slope after that. Okay, so next up, I want to place my points of inflection. It doesn't really matter where it lives. Well, I mean, it gives you a little pair for 0, so we can go ahead and highlight that point. But then at 3 doesn't tell you where it is, so just wherever your graph landed at 3, just go ahead and highlight that point. Kind of gives you a target point to know where your graph is going to change its concavity. So now go back over and retrace my graph with the appropriate curvature. So everything to the left of 0, I want my graph to be showing me concave up. So that's this part of the graph, concave up. Then my graph is going to switch over to concave down. And then switches back over to concave up. Okay, we can also sketch the second derivative graph. I know it doesn't ask for it, but on the test, you're going to have to do that. So let's go over that. Your second derivative graph is all you need is the second derivative sine line to help you create that graph. I like to label what I'm working with here. Anything on the x-axis is a potential POI. Anything above is concave up. Anything below is concave down. Thank you. I first want to place my points of inflection on my x-intercepts. So 0 and 3. Okay. Now you don't want your graph to have this shape, okay? Because it's not going to be as curvy as the original function. And all you care about is just matching the location wherever the graph is supposed to be and just let the graph live there. But I think some students overdo it. They're trying to get these curvature shapes to show up on this graph, and that's not going to happen, right? We've already established our curvature. It's all showing up on the original graph, but not in the secondary graph. So we want the graph to live above the x-axis, but it has to come down to this point because we've already established that point there. So make our graph look like this. Between 0 and 3, below the x-axis. And to the right of 3, above the x-axis. Concave up. Okay, this sometimes throws students off because they're looking at this going, this looks like a concave up graph. Why is it looking like this? Right, and again, the shape is not going to matter, right? Because this is not the original graph. This is the original graph, then yes, this would be concave up. But we're talking about second derivative graph, so everything's going to be y-axis is now defined differently. So the shape is going to just be whatever it's supposed to be. Okay. Any topics that you specifically want to go over? Optimization. Okay. So we just did one with the box. And this is the one you're going to see on the test. You want to do another one of these? Okay. Oh, this one I just created from scratch here. So okay, I'll create another one, obviously. Or do you want to try this one again? Just kind of go through the steps. Okay, okay. So I think some of us haven't seen it yet. So I'll go through the steps for this problem here. Okay, so we want a closed box whose base length is twice that of the width. The bottom is the most expensive, is $10 per square foot. the sides and the top are the cheaper ones, $4 per square foot, and yeah, for the 4 sides in the top. Okay, boxes that have 75 cubic feet of space, determine the dimensions of the box that minimize cost. Find the cost. So we want to build the shape of the box first. And then we want to understand that we want to ultimately minimize costs, right? And in minimizing the cost, it's going to be associated with the surface area and not the volume. Okay. The reason why is because we're not paying for the space inside the box. We're paying for the material that makes up the box. So to build our surface area, we're going to find the area of all the surfaces and add them up. Okay, the difference here is that it's a closed box. So if the closed box, that means there's material at the top. Okay. So here's my surface area equation. My base, the bottom is 2x squared because 2x times x is 2x squared. The top is also 2x squared. And then I have 2 vertical sides that are shorter or smaller, xh and xh. And then the front and back vertical sides are 2xh and 2xh. Okay, so far. Now the cost equation is going to be built into the surface area. So we're going to multiply each of the areas by how much it costs per foot. So the 2x squared, the bottom is $10, but all the other sides is $4. So I'm going to multiply those costs into the size, the area of the size that I've established. So if I multiply all those dollar amounts into each of the area of the sides, I get 20x squared plus 8x squared plus 4xh plus 4xh plus 8xh plus 8xh. Get it all the way cleaned up. Could be 28x squared plus 24xh. Put a star next to it, because ultimately this is the equation that we want to get ready for the derivative. But we need some help, right? Because that h is sticking out like a sore thumb. We need to find a way to get that h to be replaced. And what other formula is available for us to use to help us make that replacement? It's going to be volume, right? Because they give us, problem gives you the volume of that box. If I can set up an equation involving volume, then maybe I can find a way to replace that h, and I can get my cost equation down to just in terms of x. So my volume is 75 cubic feet. My volume formula for the box is length times width times height. So 2x times h, which is 2x squared h. Okay. Replace 75 in for the volume. Divide by 2x squared. Clean up your expression and solve for h. So 75 divided by 2 is 37.5. The x squared stays in the denominator. Now I can substitute that 37.5 over x squared into the h of my cost equation. So from here, everything should feel more familiar because we know how to find the critical points, right? You get the expression ready for power rule, find the derivative, set equal to 0, solve for x. And once you solve for x, you pretty much are near the end of the problem. You just have to reread the problem to decide, what do I want to do with that x? Do I need to find the other dimensions? Do I need to find the cost? Right. And once you solve for x, you're just inserting into one of the equations you've already established. Okay, you're not creating anything anymore. You're just finding information. So once I get my cost equation, I do want to get it ready for power rule. So I want to clean this mess up. So multiply the 24 and 37.5, take out one of the x's. The 900 over x is not quite ready for power rule, so I'm going to pull that x up to the numerator. Now this is nice and ready for power rule. Okay. Go ahead and go through our derivative. Go to power rule for both terms. Set equal to 0. And solve for x. We set the expressions equal to each other. Cross multiply. Divide by 56. Take the cube roots. Solve for x. And once you solve for x, the problem says find the dimensions and find the cost. So my dimensions is x and 2x and h. So I can double that to find the width or the length rather. And then I can also plug that x into my h equation to find my height. And then it's also asking for my minimum cost. I'll take my x value, insert into my cost. Okay, questions? Which step were you stuck on?
It's about the like line by ops, and then like find it.
How do you feel now?
I think that's better.
Because if you can build this equation, the cost is going to be given to you in the problem. So you have to every area has to be multiplied by that cost. So once you get that cost equation going, get that volume equation going, that's